And so we're studying types of data. Okay. So we'll punch that up here and get this going. When we start talking about types of data, here's some definitions I want to make sure we understand. Okay? So population, sample, and then you see two more words there that we've talked about already, right? So what's the difference? A population versus a sample. We've talked about this a little bit already, right? So population, right, is a very large set. And should I say it's a set of data? Sure. It's a very large set of data. And usually the idea is it's too large to handle. So we've seen examples of populations. And we've also seen examples of samples, right? This is a set of data we can handle. Now, can samples be large? Well, yeah. I was making that point yesterday with the polling example where we were trying to figure out what the state thought. So I did a sample of 7. We can handle that by hand. And then I did a sample of 30, and then I even did 300. And the idea was, as the sample size increased, maybe we get better results, right? But what happens is that you can only do what you can do. There's a reason that this class is taught in a room full of computers, right? Because it allows us to handle larger samples and get better results, right? So I guess what I'd like you to do, I'm going to pause here for 3 minutes, because I honestly think this is worth the conversation. You guys look tired. You haven't said your good mornings. So say good morning to someone near you. And what I want you to do is this. See if you can either from memory, from notes, or from the book, each come up with 2 examples of populations and samples. So we can see what are some different examples we might have. All right? 3 minutes I said I'd give you. Now, you guys, the name of the course, statistic, that's a vocab word, right? And the one that goes along with it is parameter, right? Statistic goes with which one of these? Yeah, statistic goes with sample, right? A statistic, we know, is some kind of a number, right, associated to a sample. Whereas a parameter is a number associated. You know, it's funny, that's probably bad language. It's probably say with, right? With a sample and with a population. I think my English is a little bit better if I do that. So I have a statistic and I have a parameter, and I've talked about population and I've talked about sample, but I didn't get the examples from you guys of these things, and so let me just kind of go around to each group. Jamie, Amy, you guys want to start? What do you have for a population sample? Anything good? So, okay, I will say when we talk about presidential race, you can talk about the presidential race you can look at what the nation thinks, right? And I mentioned to you guys at noon today, I'm going to be going to a talk talking about why did we predict incorrectly? Most polls got it wrong. But even the day before the election. Why? Okay. And so I'll have a little more info, I think, about what people think after today. There's a professor from Hiram College who's coming to talk. Okay. And when you said sample, it's interesting because I heard you mention the state. But the sample, of course, has to be a set of data we can handle. Are you able to interview everyone in the state? What's that? Oh, Cleveland. Are you able to interview everyone in Cleveland? It's interesting, right? Go ahead, Russell.
Why not take it like an individual class here at Lakeland?
So I could interview everyone in a class, right? I could take the 14 of you and I could interview you about the presidential election. Let me ask you this. If I did use this classroom as my sample, do you guys think that would be a sound way to figure out what's going to happen across the nation? No. Okay, so we have that understanding. Okay? So it's interesting. How we come up with samples that work, that's part of my job today to explain. It's also section 4. Okay? But this is cool. At least I have an idea. And let me go over to Brandy and Sarah. Do you guys have another population or another statistic or parameter that you guys talked about that we want to mention? What was it?
Like class here compared to university.
Oh, okay. So you could be talking about a university. That would be a population, and maybe one class. Okay, that's interesting. And that's what Russell was mentioning also, I guess. Okay. Sierra and John, did you guys come up with anything that's not up here yet?
Kind of. I couldn't figure out the sample, but the population was like the number of job applicants.
Okay.
And then,
So we could say job applicants for what kind of a job were you guys thinking? Or maybe you didn't specify. I don't know.
It wouldn't even have to matter, wouldn't it? I mean,
because you can still pick a certain amount of people out of the applicant, so that would be like the sample.
So I see what you're saying. You have a job applicant pool, and maybe instead you look at some of them.
Yeah.
Okay. I understand.
That's right.
I'm trying too.
it would have to be something related. Even if you pick class-wise, to say if you did a poll for the whole school would be the population and the class would be the sample, but it depends on what you're talking about too, right?
Well, yeah. So maybe that's a question I should ask too. If we are talking about the university, what would we be measuring? And there's a lot of things we can measure, right? The test scores. We could look at test scores. We could look at GPA. We could look at age.
Right.
We could look at blood pressure.
Okay, so with the job applicants, you can look at experience.
Okay, so we could say number of years experience on their resume, let's say, right? And by the way, if you looked at the entire pool of job applicants and you had the number of years experience, maybe you could compute something about them, right? A measure of center or a measure of variance, right? Or other things. There's other statistics and parameters also. Yeah, maybe what I want to talk about now are statistics and parameters, right? Let's say we're talking number of years experience. Number of years of experience for a minute, right? So you could get this job hunter has no experience. This job hunter has 20 years experience, 3 years, 2 years, 7, right? And you could compute the mean. Well, could you? Out of the whole pool? Maybe. I guess if you have it, all the data for the pool in one computer file, then you could. But if it's too big to handle, that's when I start saying that's a population. It's very large, too large to handle. Okay? Now, do you remember the Greek letter that we use for mean when we're talking about, a parameter? Mu, that's it. Mu. It's the Greek letter M, stands for mean, right? So this is the mean. But along with a parameter, we also have a statistic. And the idea is maybe there's if we just take a sample, if I just take one class, maybe I could take that average number of job years of experience. Right? We could do that. So if I got the number of years experience that Martha has, that Laura has, that Lita has, that Jawan has, and I just keep going, I could take that average, and what's the symbol we use for that average? That mean? Not O. So in general, we'll use Greek for parameters, but for here we don't. Have you guys remember this symbol? It's been a while. Yeah, it's been like 1 week. No, it's been a while. It's been 2 weeks. Right? That's called the mean. We also have a measure of spread or variance or standard deviation. Do you remember what letter we use for standard deviation? It's not hard.
It's like an O.
Well, this one's S. And the other one, yes, it does look like an O with a squiggle, but it's actually the Greek letter S. It's called sigma. That's the Greek letter S. Believe it or not, actually it kind of looks like a cursive S if you stretch your imagination a little bit. Right? You know what's funny is the Greeks also had a capital S that you've seen before, right? We use that for sum. So these are just some parameters and statistics, and there'll be more as we move along. I think that's enough for now, okay, for me to kind of show you, hey, this is the stuff that was on your first quiz that I haven't talked about yet. I'm like, oh, I skipped chapter 1, paid the price. Okay. That's where I give you those extra points back. So those are some key ideas from chapter 1. There's some other vocabulary that I need to get across when we're talking about types of data. Okay? And so one of the ideas is this. Yeah, quantitative versus categorical. So quantitative data, that's numbers. Guys, I think this is where I'm going to live in this course for the most part. Numbers. Because that's what I can help you with. But you should know that sometimes we also talk about categorical data. Actually, you guys did today. Categorical data is other. So an example of categorical data would be which presidential candidate do you prefer? Right? That's not a number. It's not like the average voter liked Trump and a half. You can't say something like that. No. Right? You're gonna write down something that's not a number to a question like that. And we can monitor that data, but that's not numerical data. Actually, gender, right? When I ask for your gender, male, female, we're not going to have some kind of a number with that. But when I ask your age, or when I ask your blood pressure or your height, we measure these things, right? These are numbers. And even within numerical data, so we're going to live here, guys, okay? But even within numerical data, you should know that numbers are different. What I mean is, there are different levels of membership, levels of measurement, measurement. And I think there's some really nice exercises in the book that I thought I'd walk us through to kind of demonstrate what's going on here. But the 4 levels of measurement, these are all on page 20 of your book at the bottom. And so if you want to look at that chart, that's fine. I'm going to pause and pull it up on the screen so we can look at it also. Hey, even before I cover levels of measurement, I'll do that next. There's another way you can split up data. And maybe I'll do that down here at the bottom, and then I'll come back to levels of membership. Levels of measurement. Wow. So I want to talk about these 2 words. You've seen them, but we haven't really. Discrete versus continuous. Okay? Discrete versus continuous. You guys remember we were talking about the binomial random variable, right? The binomial random variable counts, so I'll say X, counts the what? Do you remember what it counts? The number of, we called them successes, right? You guys, what's the smallest that you could get for the binomial random variable? I guess 0, right? What else could you get? You get 0, or you could get 1, or you could get 2, right? I guess you get up to whatever n was. But this is an example of what is discrete. And the reason it's discrete is there are gaps. What do I mean by gaps? Binomial random variable, you count the number of successes, but you cannot have x equals 3.7, right? You can't have 3.7 successes. You either have 3 or 4. You guys with me on that? So when I say there are gaps, what I mean is if you were to list all on the number line, all the possibilities, well, you could have 0 and you could have 1 and you could have 2, etc. But the gaps are in between those. You can't have 1.5 and you can't have 0.5. Those measurements wouldn't make any sense if you're counting a number of successes.
So there are gaps, or there are not gaps?
I don't know how you want to say that. I said there are gaps, but what I mean by that is the random variable can't equal certain things. An example of a continuous random variable, in my mind, would be this. Suppose y is measures length in inches. Well, now, when I look on the number line, okay, you can have a length of 0, I guess. Could you have a length of 1 inch or 2 inch or 3 inch? Sure. Can you have a length of 2.5 inches?
Yeah.
That makes sense. What about 1.7? Yeah. And actually, I claim that you can have a length of any number on the number line. Does that make sense? You could have a length that's the square root of 2, and that's 1.4 something. And this is an important idea. There are fundamental mathematical differences when we're talking about discrete and when we're talking about continuous. Okay? One more thing and then I'm going to get some questions. Chapter 5, when we talked about probability distributions, and we talked about random variables. Chapter 5, it was all discrete. Okay, it was all discrete. But chapter 6, we're actually going to get into continuous because some of the most important distributions are actually continuous. Last thing for me to say, and then I'll get questions. You guys, I teach a class here called Finite Math. You could take if you take college algebra first. A lot of our business majors take it. Everything we do in that class is discrete. I also teach several different kinds of calculus. Everything they do is with continuous functions. Okay? Now it's interesting because now I'm teaching statistics. Well, we need both. We need to know a little bit of the difference of both. So now I'll take questions and then I'm going to go to these examples of data that you guys have and we'll try and say which is which. Okay? Laura had a question.
Is continuous considered more specific?
What do you mean?
Well, if discrete can have gaps because it has to or maybe some would continuous be more specific because you can have like decimals? Or can you not really compare because...
Now I understand what you're saying. You're saying like when you make a measurement, there's always rounding that happens, right? And
two data sets are just like different. Like
I think here's the difference. You guys, if I'm storing lengths in inches in my database, Laura's pointing out that you're probably not going to write the square root of 2. You're going to write 1.4, right? And so you're rounding. And then you might write 1.5 for a different measurement, but you're never going to write 1.4776234. You see what I'm saying? Even though that's a number on the number line, we would never write it. We're going to round. So I would say that length is continuous, but you're right, we're going to round it to some decimal point. What about this, though? I'm saying when you count a number of something, it just can't be 3.7. It's not that I rounded it to 4, it's just it can't be. You're counting a number of something. Does that make sense?
yeah.
So I guess the question is, are we, these different data sets we have, are they discrete or are they continuous? Here, let's make a little list here, all right? I'll say discrete, and I'll say continuous. So Kelsey, let me go to you and Dylan. You guys were talking for a little bit. You guys come up with anything we can measure.
Number of meals.
What'd you say?
Number of meals.
Number of meals. Would that be discrete or continuous? I would say discrete, right? I mean, I go to the church, I volunteer, I'm going to serve, 34 meals at this retreat. It's not going to be 33.36. We don't do that, right? We just count numbers. What'd you say, Martha? Score of a game. The Indians won last night 4-3, right? I like that. So scores in games. Lita, you and Jawan have an example of something you can measure? Oh, yeah.
I had said, ages.
Ages. Now, here's an interesting one. Are ages discrete or continuous? So, yeah, that's interesting, right? Because if you ask me how old I am, I'm going to say 44, right? I'm not going to say, well, actually, guys, I am 44 and a half plus a little more. Oh, it's my sister's birthday today. Well, we know this because we're 1.5 years apart. But mine's the 3rd, not the 5th. I got to call her. All right, thanks, Franny. Anyways, back to the point. We treat ages as discrete On the other hand, right, time, if we say time, that's continuous, right? Like, we'll talk about 2.5 hours or a quarter of an hour, right? A third of an hour is 20 minutes. That, I would say time is continuous. Any other examples you guys want to ask about? And then I'm going to move on to the levels of measurement next. Years? So it's funny, if I say years, now I'm counting them. Although, could you have 2.5 years? I guess so. Yeah, I think time is continuous. Something else that I would put under the continuous? How about temperature? Right? I mean, how hot is something? Right? Anything else? Questions?
Weight will go under continuous.
Which one?
Weight will go under continuous.
Yes, weight we would put under continuous because something might weigh 2.5 pounds or 2 3/4. And at that point, what we usually do is then we'll switch. We'll measure it in ounces, right? Yes?
Sorry, I wasn't here for the discrete and continuous. So is discrete basically any like anything that like I don't know can change in value like kind of erratically, and then continuous is like
Yes.
you know.
Yes, erratically is one way to say it. There are gaps between the possible data values, right?
Okay.
Whereas continuous, you can take on any number on the number line. That's the
Okay.
difference.
Got it.
For me, I like to draw the number line and say what's possible. That's how I figure out if it's discrete or continuous. Distance, I would say, is continuous. I agree. You could have 2.5 miles, 2 3/4 miles. Of course, distance, that's the same as length, right? Yeah. So, okay. But let's go on to the levels of measurement. I think these are interesting questions. And so, I'm going to be talking about, really, this is from page 22. But first, let's look on page 20. They list the levels of measurement, and then I'll talk about each of those with you. So, here's the chart. Let me zoom in just a little bit more for you so that everyone in the back can see as well. Oh, not that much. So, if we look at this chart, here's the 4 levels of measurement, right? Nominal, ordinal, interval, and ratio. They put them in this order. They say ratio is the highest level of measurement. Okay? I'll put them in our notes the other direction, but I kind of like how they do this. Okay? So when we start talking about levels of measurement, nominal. These are numbers that have no meaning other than, I'm sorry about that, that's off the map. Maybe I should say it this way. To name something. So, the example the book gives in their little chart at the bottom here, eye colors. So, nominal, they say eye colors. Okay. Right? Blue, green, brown. Right? Eye colors. It's funny because I said numbers. Could we give a number to different eye colors? Sometimes computer people do that. They'll say, well, number 1 is blue. Number 2 is green. Number 3 is brown. But it's not like these numbers have any meaning. It's almost like just a shorthand way of, like variables. Yeah, you're just naming the colors with numbers. You know, it's a category. You'll see this on a computer, a drop-down menu, right? You know, choose your school you want to send your transcript to. And for some reason, I still remember my undergraduate college, it was 1841. I had to send them my transcript. I don't know why. It doesn't mean anything. But it's a number. Your social security number. Nominal. It's not like the number means anything. It just represents your tax money, right? Or something like that. Your birthday. Yeah, I could see that because it's just, it's a number, but it's not. Although it might birthday may fall into the next category depending on how I think about it. Let me show you the next category. The next category we would call ordinal. Okay? And the ordinal level of measurement, what's the root word, right? Data can be arranged in order. Okay? So now, we can order the data, but subtraction here is meaningless. Now, before I start fielding lots of examples, I want to put the other two categories up also. I'm going to give you one example of each that the book gives. I think that's smart. Here. Ordinal says, ranks of colleges in U.S. News and World Report. Right? So we can talk about ranks of colleges. And they say the number one college in the United States is? What would you say? If you had to guess what U.S. News and World Report is going to say. Yeah, okay. Well, I guess we don't read that. So that's a bad example. How about ranks of? How about ranks of basketball teams?
There we go.
Now we're talking. Right? Who's number one?
I mean, the Cavs are biased, so.
The Cavs. Who's number two?
Selfish.
Who's number 8? That's the important question. Isn't it true the top 8 make the playoffs?
Yeah.
The top 8 make the playoffs. On each side, I know, yeah. I was just thinking Eastern Conference. All right. Next. More than ordinal, okay, would be interval. This is a higher level of measurement than just being able to order the data. Okay? So here it says, differences are meaningful. Do you know what the word difference means? Yeah. Now we can subtract and learn things. But division would be meaningless. So just like, you know, if we say the Celtics are number 3 and the Cavs are number 1 and we subtract, we get 2. Does that mean we're 2 better than the Celtics? It doesn't really make any sense. All I know is that we're higher up than the Celtics. That's what that number means. Well, sometimes you can subtract and it makes sense, but dividing does not make sense, okay? Let's see what the example is they give. Temperature. Yeah, that's the one I usually think of. The example I think of is temperature in degrees. And this is either F or C. Fahrenheit or Celsius, right? So you guys, yesterday the high was 60. Today the high is 50. And so that means if I subtract, Does that make sense? It's 10 degrees colder. Is that true? All right. But here's something that doesn't really make sense. If I say, today it's 40 degrees and tomorrow it's 80 degrees, it would not be precise to say that's twice as hot. That's not true. I know 80 is 2 times 40. I get that. But it's not true to say it's twice as hot. That's not accurate. Okay? It is 40 degrees warmer. But one of the reasons that twice as hot would not be correct there is because there's one other thing about interval that I think is a good giveaway. And that is, there is no meaningful zero in interval. What I mean by that is, yeah, we could talk about 0 degrees Fahrenheit, but do we ever have negatives? Sure. We live in Cleveland, right? Or my buddy in the Netherlands, right? You guys know what 0 degrees Celsius is? Same as what? 32 here, right? Because it's where water freezes. Quite often they'll be in the negatives in the winter, right? So it's not like, you're twice as warm if you're at 2 degrees instead of 1 degree. That's not true, okay? So that's a way of understanding interval. And then the last one is ratio, the highest level of measurement. There is a natural zero starting point, and ratios are meaningful. So now, since there is a natural zero, ratios are meaningful. You can divide. And so they give lots of examples here. Let's see what they give. Height, length, distance, volume. Okay? So that's the highest level of measurement, I guess, would be ratio. Heights, volumes, etc. All right. So I thought maybe as practice we'd do a few of the even exercises, and I assigned some odds for homework, just to make sure that you guys get this idea. And then we're going to move on to the final section. So here's the homework. Well, actually, I can do better than that because we have the book right here. Let's go through a few of these from page 22. Okay, so question 22, right? You say, which of the 4 levels of measurement are we talking? So here we go. 22. Depths, kilometers of earthquakes. Oh, I remember that data set. That's the one I was having trouble finding that one day. Right? So do you guys think that when we're talking about how deep an earthquake is in kilometers, is that nominal, ordinal, interval, or ratio? Ratio? Yeah, that's a distance, right? Could one earthquake be twice as deep as another earthquake? Yeah. And could you have a depth of 0? That would be right at the surface. So I agree, 22 is ratio. Guys, I think I'm going to pause, and I think it's worth 2 minutes of our time to do the next 3 even questions with someone near you. 24, 26, and 28. And after we do those, then I think we will move on. Okay, I'm going to go back and write down. So another example of ratio, right? We have depths of earthquakes. That works pretty well. Now, what about, do we have examples of these other ones from the problems you guys just did? Any that are nominal?
Yes.
Which one?
The car model.
Car models, yeah, right? They're just names only. So that's clearly nominal data. We had eye colors, now we also have car models. It's nice to get some other examples, right? So you could have Buick, Skyhawk, right, or something like that. You could have a Ford Escort. That was my great car when I was your age. All right, so anyways. What about ordinal or interval?
Interval
24 is ordinal. I think so, right? A 4-star rating. Does that mean it's 2 stars better than a 2-star rating? Yeah, but it's not like you're going to subtract to figure out how much better. All you know is that 4 is better than 3, 3 is better than 2. How much better? It's order only. It's not interval. All right. So yeah. So what do we call those? Movie ratings, right? Would be ordinal. If we're talking about number of stars, right? 4 stars, for example. And then another example of interval. What did we do? Oh, those were body temperatures? Okay. So body temperatures, yeah. So anyways, I think you have enough now that you could probably work through the entire section of homework of section 3 without a problem. Okay. So any final questions on this kind of stuff? Okay. Let's move on to section 4. And here's where I want to talk about sampling. Collecting sample data. Oh, funny, it says 5.
So what is the homework?
That's on Blackboard. You'll see it on the listed. So, yeah. We're going to do some definitions here also. Bless you. So this is 1-4. Collecting sample data. And so the first definition I want to give you is what's called a random sample. A random sample. You guys will see quite often in the book, we are going to say, suppose we are able to generate a random sample. A random sample this is a sample in which every member of the population is, and maybe you know what I'm going to write, there's a 2-word phrase that I've been writing a lot this year that goes along with the word random. It also has to do with probability. Equally, do you know what the other word's going to be? Equally likely is what I'm going to say, to be chosen. So here's the key phrase, random sample. So every member is equally likely to be chosen. All right? So it's interesting because one of the first things we talked about when we were talking about examples of populations and sampling, we talked about the entire college, Lakeland Community College. That's a population. If I say, look at this class, would that be a random sample? The reason I'm going to say it's not is because I claim that if I do that, if I just say, look at this class, there's some people had no chance of getting picked, right? For example, people I don't teach, right? People that come to school only on the weekends or only at night had no chance of being selected if that's how I do it. Does that make sense? Now we could do it a different way. We could say, how about we take all the teachers and we pick a teacher and say, hey, take one of your classes. Right? Even then, it might not be a random sample because some teachers teach more classes than others. So if you picked me, I'd have to choose out of my 4 classes. But some of the teachers that are part-time only teach 1 class. If you pick them, in a sense, their students are more likely to be picked. Like, They might pick me and I still don't pick you. You see what I'm saying? This is not easy to come up with a random sample. But the strange thing is, a lot of the theory that I'm going to present only applies if we truly have a random sample. You guys, I'm going to a talk today about the presidential race. One of the things I have heard about the presidential race is the sampling was not good. There were a lot of voters who the people doing the polling were not able to reach. They still came out and voted, but they might not be the kind of people that you can reach on the telephone through telemarketing or that you can reach on the internet. But they voted, right? And this may be, it may show that the sampling wasn't truly random when they were doing the polls. That's kind of interesting. But actually, we need more than just a random sample for much of the theory to work. We actually need what's called a simple random sample. And this may be one of the harder concepts to explain in chapter 1. I'll write down the definition and I'll do my best. And then we'll work on the homework tonight and see where that goes. So a simple random sample of size. What letter do I usually use for sample size? You guys noticed yet? What letter I usually use for sample size? It's n, lowercase n. We're usually going to use that. I'm just trying to get you guys, when you see the letter n in this class, that's probably sample size, okay? A simple random sample. This is the definition I'm giving now. We did random sample. Now I'm doing simple random sample. So we'll say it's a simple random sample of size n means we have a random sample where every possible sample of size n was equally likely to be chosen. And that might at first glance seem like almost the same thing I just said up above. But I'm going to highlight what the difference is. See this right in here, guys? These last two lines? That's what I'm looking at. Every possible sample of size n was equally likely to be chosen. Now, imagine this. We want to survey our population of statistics students. Okay? Suppose Lakeland has 5 statistics instructors this semester. Each one of us has a class of 15. Right? So what we could do is we could talk to Professor Shikani and myself and the other 3, and we could say, all right, there's 5 classes of 15. Let's just take your 5 teacher names, put them in a hat, pick one out, and whichever class we get, that'll be our sample of size 15. That would be a random sample, because each one of those 5 classes would be equally likely to be chosen. Actually, every person in the class would be equally, right? Every statistics student would be equally likely that they're chosen. But that would not be a simple random sample. The reason is, to be a simple random sample, every possible sample of size 15 would have to be equally likely to be chosen. And one sample I could imagine might have 3 people from my class, 3 people from Professor Shikani's class, and 3 from each of the other classes, right? But if you do the sampling the way I suggested, will that ever happen? No. We said we were just going to pick one person's class. Now, picking one person's class, a lot easier, right? Doesn't take as much work. But for the theory of statistics to work, you truly need a simple random sample of size n. You'll see in the theorems. It'll say, if you have a simple random sample of size n, here's what's going to happen. Now, polling institutions that, have you guys ever heard of this group? The Gallup poll, for instance? Have you guys heard of this organization, the CDC? I bet some of you know what that is. What's that? The Center for Disease Control. It's funny. Putting these two next to each other is kind of funny. Because are they related? The only way they're really related is they both make massive use of statistics. When the Center for Disease Control does a study or talks about a study, it better be a very carefully planned study with control groups and things like that. And usually what we do is we take a simple random sample, but it takes a lot of work and effort to get that to happen. Okay? So what section 4 is all about, that I'd like you guys to work on tonight, is all about sampling. And once again, what I thought would be good for us to kind of finish here is I want to do some of the even exercises with you and talk about, do we have a random sample or not? Do we have a simple random sample or not? And those are very nice things to talk about. Okay? Here, actually, before we do that, there's actually a chart with some examples of some different kinds of sampling. I saw it. Where did it?
25 with the email.
Yeah, 25. Let's look at that. Let me go to page 25. Thanks, Lita. Okay. So they say, here's some different kinds of sampling. Actually, this first picture kind of cracks me up because it says random sampling, right? Computers are often used to generate random telephone numbers. Actually, there's a big debate. When a computer gives you a random number, is it really random? That's an interesting question. I think the first day of class I had you guys write down random numbers, but I hadn't told you what I meant by random yet. You know what's random? When I shuffle the cards and you pick a card, that's random. Because each number is equally likely to be chosen. You have no way of knowing which number is which. As long as I really shuffle. Right? And simple random sample, you have to have, like I said, any sample of n has to be equally likely. Let me give some other examples. Here's one. Systematic sampling. All right? So let's take, what are they doing? Every time people are walking through the door, every third person, let's give them a survey. That would be a sample, right? That'd be one way of sampling. Would that give you a random sample? I'm going to say no. Why not?
Why not though? That's random people. You don't know.
You don't know who is. You're right. But the reason it's not a random sample, what's the definition of random? Random means...
Everybody has an equal chance, so they.
And I'll tell you who doesn't have a chance here. That early bird. That person that's always first. First in line, right? No way are they going to be chosen this way. Because you're only choosing every third person. And so the first two are not going to get chosen. They have no chance of getting chosen. You see what I'm saying? There can be bias against that person that's always there early. You're not going to get that. Convenience sampling. Hey, I'll just take the first row. I'll sample you guys. That's not fair. That's not random. Here's two others that are used a lot. People do this. People do that. But you should understand, when you guys read about a study, if you see that they used systematic sampling or convenience sampling, please understand that the results might not be as accurate as if they could get a simple random sample. Here we go. Stratified sampling. Strata, I always think of clouds because I remember the stratosphere, right? Layers. It says subdivide the population into at least 2 different subgroups or strata. So that the subjects, such as gender. Hey, we could do that, right? All the males raise your hand. All right? And I could survey a sample of males. So I'll take 2 of the males. All the females raise your hand. And I'll take 2 of the females. Would that be a simple random sample if I do that? Because it's a subgroup of size 4, but I could never get one with all men, and I could never get one with all women, so it's not a simple random sample doing that. Here's a question. Would it be a random sample? Is every person equally likely to be chosen? So, yeah, but Dylan has a point too. What were you saying?
We have the same amount of guys and girls.
Do we? I don't know. How many men are there? Can you raise your hand again one more time? So I count 4, 5, 6, 7. So I guess the chances of being selected if you're a man are 2 out of 7. And how many women do we have? Let's raise your hand. 1, 2, 3, 4, 5, 6, 7, 8. The chances of being selected if you're a female in this class would be 2 out of 8. Today. So today, if this is how I did it, I claim it wouldn't even be a random sample because you're more likely to be chosen if you're male today than if you're female today. You see what I'm saying? Even to get a random sample is not easy. Why would people use stratified sampling? Why might we want to ensure that the committee has both males and females? To prevent bias against one of the genders, right? That's one reason. Another reason. Maybe it looks better politically, right? If you're going to have a group subgroup's going to make decisions for you, again, you may want to make sure everybody's represented just from a political standpoint. Right? So sometimes there's reasons not to go pure random sampling. Okay? And you have to balance all this. Here's another way people do sampling. Cluster sampling. So divide into clusters and then choose everybody. So like this, guys, I'm going to select one row randomly, row 3. And I take everybody in row 3, and that's my sample of the class. That's called cluster sampling. We are out of time. You guys can work on this homework tonight. We'll talk about it tomorrow. If you have any homework for me, bring it on up on your way out. I'd love to have it. Thanks, Russell. How'd it go today?
It went pretty well.
Good.